Hello to everyone. I'm very happy that you are there. Thank you to arrived to this 6th event of the PRELUDE Educational series. And today what we will speak about and what we will treat is the topic of building climate resilience. Where we are, inside the PRELUDE project, which is a EU co-founded project with the European Commission, we organized a series of educational events. Among them, this is the 7th event, the last one that is organized in that way. And as you see, the event was about forecasting, building optimization, digital twin, smart building in general, data treatment, etc. But we also have 2 moments in which we have focused on climate design and low energy design, which are also topic of the PRELUDE project because we explore and try to maximize the controlled use of free-running buildings. Inside these, we have a first event of urban climate dimension, in which we generally introduce the urban island problems and others speak with professor from Barcelona, professor from Chile, Valparaiso, and so on. But this year, we will have again a meeting on the climate resilience point of view, so climate change and impact of climate change in the different aspects. Clearly, we start, and we will have in this case, 3 presentations. Before arriving to that, I only short recap where we are. The PRELUDE project operation, building operation, utilizing real-time data for energy dynamic optimization. Some of the audience already know because we're there for the 6th event, is a project that supports smart building and low-cost solution. So it's an applied project, research and innovation, innovation action mainly, that has a scope to minimize the energy use, maximize the use of self-consumption, but especially maximize the comfort by focusing for what it is possible free-running potential, or self-action of the building to and of the user to do the action to protect their environment for external conditions. It developed a modular platform supporting data integration by different modules that is quite complex, and allow to support forecasting and optimization of building elements and consideration not only in the real time, not only based on threshold logic, but based in adaptive forecasting. So prepare the building for what will arrive in the near future. We have a lot of demo cases in Denmark, Italy, Switzerland, Poland, and Greece, and a living lab in Austria. In addition to that, in Denmark, we also have a city case, an urban case, which is a district heating control logic. But inside this aspect, we also have climate change resilience. There is a specific task for that investigate the impact of climate change on building design and operational choices with specific indicator. And that's the topic that we will treat today with our 3 lectures. First of all, today what we will do, we will focus on climate change. We try to introduce the climate change dimension thanks to the presence of Professor Jost von Hardenberg. And inside that, we try to understand what also is arriving on upcoming global climate models. So where we get the data. When we speak about climate change, we know, roughly speaking, what it is, I hope. Do you know? Everyone has spoken. We are architects, especially our architect engineers, so clearly we will face the problem, okay, with our design. And it's also important to know where we say, and we will do this analysis, where we get, or where we are in terms of data. After that, we will discuss some innovation and studies on building climate change resilience, how to integrate the urban dimension, the urban island, and how this impact our design choices if we do and we will not do. And last but not least, we also discuss some lessons learned inside the PRELUDE's climate change resilience approach that analyze how is expected the modification in some of the most recognized key performance indicators of built environment analysis, climate design, climate bioclimatic design in the future and in the past 50, 70 years. Well, speaker recognized expert. In this case, we are 3 main speakers, 3 main interventions, okay, by the academic domain. The first is a speech by Professor Jost von Hardenberg. We are at POLITO DIATI department, former first researcher CNR, okay, which is a full professor of hydrology and hydraulic. What does it mean? Climate model, I think, in theory, yeah, exactly. It will address to us the climate change dimension, because we always look and listen to that, but I think it's very important to have a fixed point on that. And after, we also show to us, I think, some global numerical model where we go in this sense, which is the breakthrough approach, is now this new idea. After that, we have an intervention by Professor Maria Kolokotroni from the Brunel University in London. Again, in this case, she leads the Research Center Resource Efficiency and Future City of this Institute of Energy Future of the Brunel University. A member of G.Chiesa, A.Jahanirahaei, we work together inside the EIBC Annex 62 and 80. So ventilative cooling and resilient cooling. She is very active in European projects. And she will present to us today we can say, the urban impact. Because we have done, or we know, I think, as audience, the major audience that I see that I know, that works in climate design, start experiencing the impact in between climate and design choices and design operational choices. But we do not have touched, for example, the urban dimension. And we immediately see that when we pass to a typical rural side to the urban side, the context changes. Because not only we have the surrounding building, but also the type of climate or weather typical characteristic around are different. And that's what we will speak about. After that, we have the last presentation, again, by POLITO, in this case, the architectural department. There is me, there is P.Carrisi, and A.Jahanirahaei that will do the presentation. And this will be about an approach, that integrate in some way the result of global and regional climate change models, okay, with the built environment to support analysis that start in the 50 with the reanalysis databases and arrives to 2100 with all of the errors of the models, but to give the idea of which is the climate, like as I mentioned. There's no more a fixed element, We generally collect one climate data, we use that, we do the design. But this is not really true, because the climate is fast showing a variation. It's typical weather condition, but it's not a typical weather condition that if we take the Gianni De Giorgio database now is still valid for building design. Okay, this 50 here, I totally changed the approach. So that's what we will look inside. Only need to remind us last things inside this introduction that clearly this educational event series is part of a large dissemination series of action that include citizen science with 6 schools monitoring the Piedmont region. We are reaching more than 1,000 students, etc. in the school for indoor air quality control. We also support a smart building educational project with more than 10 projects with multidisciplinary students' involvement in the POLITO, and that will be clearly presented in a sort of final event at the end of this year. Now is the moment to leave the floor to Professor Jost von Hardenberg.
Thank you for the introduction. As said, I'm working mostly on, actually I'm mostly a numerical climate modeler. And so I work mostly on the development of numerical climate models, and then of course on the study of the results, the application, and then there are different fields of interest in which I am currently working, analyzing of course the what the output and the impacts and the projections of numerical climate models. What I wanted to do today, though, is rather than giving you more general talk about climate change and numeric projections by the numerical models, which is something which you may have already heard or you may hear easily, I wanted to focus, well, a little bit on what are numerical climate models, because those are the main tools which we are currently using for a range of goals. But basically, they are one of the main tools which we are currently using also to inform policy decisions, mitigation decisions, and adaptation decisions for the future in view of current and future climate change. And so what I wanted to do is to give you a brief overview of numerical climate models. Then rather than showing you what the current generation of climate models is projecting for the future, which is more or less a usual thing you might see, to continue actually giving you an overview of what is happening in the community nowadays. So what is the latest developments? because we have some quite interesting, if not exciting, developments in terms of new models and new ways to do climate modeling, which we are developing. And so my hope would be that this talk would give you sort of a feeling of what is the current state of the art / what will be the state of the art in a few years. So that you can see which tools you have either available now or you might have available very soon. So modern numerical global climate models, currently there is this term digital twins. I will come back to this term, that they are also considered digital twins of our entire climate system. I will come back to that a little bit later. But basically, they are obviously a representation of the climate of our system. They allow us to have at each instant in time, for the past and in the future, a representation of the climate situation of the planet. Being climate models, they do not attempt to do weather forecasting. They do not try to reconstruct what was the weather today. They are trying to reconstruct what was the type of weather, the variability of today. So they will give you a representation of one possible day in June 2024, not that particular day. But apart from this, these tools are fundamental because then we can do many runs of these numerical models. And we have all the possible fields. They provide us temperature, pressure, precipitation. They are all correlated. They are all consistent with each other. And basically, we can look at these models. In fact, we modelers call these numerical experiments because we look at them as if they were actually experiments in a lab, because you can go there and take measurements, extract data from the models, and get completely consistent time series, fields, maps, etc., for any place in the world and for different times in the past and in the future. And obviously, having such a tool, we can use them for many goals. And the main one for which they have been developed is basically to, they have been developed mostly by physicists and engineers, but mostly by climate scientists, to study the mechanisms of climate change. So to understand the physics, to understand what is happening in the climate system, and how and why certain phenomena are possibly also how they work, what are the main mechanisms of variability in the climate system, and also how a certain phenomena might be changing in the future, certainly, but basically understanding the main physical mechanisms. Then we can use them to simply do experiments where we say, okay, let's take the model, force it with current emissions of CO2 or current concentrations of CO2 and other greenhouse gases, other forcings. There is not only greenhouse gases, there's aerosols, land use, etc. We can make so-called projections or future scenarios. We have different future stories of how aerosol concentrations, greenhouse gases, etc., might be changing in this coming century. These stories, these scenarios, are actually a very serious thing. They have been formulated by groups of experts. They have been codified, so we have a certain number of such future scenarios to explore, and based on different options on what will be the future political decisions during this century in terms of climate mitigation, and also future development of our economy, of our societies. I mean, it's a very complex thing, this creating such scenarios. But once you have them, you can force the models and say, and give to the model the forcing greenhouse gas concentrations. The model will then evolve them in the future and reply, giving us also the evolution of temperature. Notice that I give the evolution of greenhouse gases, the model responds with the evolution of temperature, precipitation, things which I wouldn't know else. To that degree. And particularly, it also allows me to have an evolution of temperature, precipitation, etc., also at a more local scale, say over Europe, over the Mediterranean basin, etc., etc. There is an issue with resolution, and I will briefly come to that very soon. But basically, this, you see how this then becomes an important tool for making policy decisions, for having these scenarios, because basically, if I can also do experiments, what if I follow this scenario, what if I follow that scenario? Different scenarios might have different costs in terms of policy decisions. I mean, literally different costs. They cost more to our economy or less, or might have either economical cost or cost in terms of change or political sustainability. And so we can, with this, explore what would happen if we end up in a future following a certain path or a future following a different path. And above all, now they're being used not only in this trivial way to say, oh, what terrible disasters will happen to us in a 2 degrees warmer world. There are many ways you can reach 1.5 degrees or 2 degrees in the future at the end of the century. The different ways how you reach them correspond to different actions in terms of mitigation. And so models can be used to explore what will happen in detail when you reach that. So you might have a future where you reach 2 degrees globally, but maybe precipitations and how you get there could be different. And then finally, you can use them to do attribution of climate change. What does it mean to do attribution? Well, basically to understand if certain phenomena, say an increase in some extreme phenomena, can be attributed to climate change, or if it is rather a natural phenomenon. Because we can do a series of model experiments to answer this question. So you see, we are really using these models as if they were digital twins. Well, let me anticipate this concept. Digital twin is a concept which comes from industry. It's related basically, say you have some machine which is in production, you cannot stop it, but you would really like to know what happens if I turn that dial to the right. I have the impression that it might work better, but I don't dare to do it, because if I do it, I may disrupt production. So if I had a digital replica of the machine, something where I can turn the knob and see what happens, then of course I can get my replies. And that's the same. We say, I cannot turn a knob for the climate. Or, of course, I could implement some measures, but before doing it, we need to know what would happen. So that's how we use it to do these policy studies. And then, of course, the models, and this is probably the only plot which I will show you to this end, the models do different future projections, and you can have, for example, future evolution of temperature, like in this plot, where you see a wide, broad range of possible futures which come from following different paths, but also doing many model runs. This includes also natural variability of the climate system. Okay, let's try to be a little bit less abstract. Let me spend 2 or 3 minutes to give you a brief history how we came to the current point, and then let me advance. So climate modeling basically has its origin in weather forecasting. Oh, I just realized there's a typo here, so it's weather, not water. But beginning of the last century, basically, the situation was that there was a broad range of measurements available, a good, efficient way to communicate them. There was already the telephone invented, telegraph was working. So it was possible to create, say, maps of pressure each day. And so physicists and climatologists and scientists in general at the time came up with the idea, well, we know everything already about fluid mechanics. Why don't we use the laws of fluid mechanics to integrate forward in time these maps, so to see what will happen next and do a weather forecasting. And this idea was then developed. There are some technicalities. The fact that you need this corresponds to integrating complex partial differential equations. That's not something which can be easily done, and so they need to be approximated. There are ways to do it. There's a way to transform them into algebraic equations, and people did that. And then there's another scientist, Richardson, and he brought an entire book on this. Notice it's a book from 1 century ago, which already was entitled Weather Prediction by Numerical Process. So it could be a modern title. And in fact, it's a very modern book. And he was assuming that this huge work of solving these equations could be solved by dividing the work among many computers. The only thing is that in 22, a computer was a person who computes, not a digital machine which does it. So the idea would have been to take these maps, give them to you, say in this room, each of you works on a little piece, little area, say little area of Europe, is responsible for that, does only the calculation there, and then the nature of how we approximate these equations is such that then each of you would only have to talk with your nearest neighbors. with your neighbors around you. And there, this works. But the nice thing is that this is identical to how modern computers work. This illustration is very nice. It was by a Belgian artist of the 70s, I believe, illustrating a modern version of this book. And, well, I like it also because this is, you see, it's a big hall, a lot of people, the central person who is coordinating and say, you please give me the result, and so on. And it looks like the Senate in Star Wars, of course. It's a funny thing for me. Okay, so after the war, after the Second World War, there was another combination of facts. The nice thing that actually suddenly digital computers had been invented. A little bit due to the war effort, of course, there was an acceleration. So at that point, we had a nice solution, digital computers, which people realized they were very powerful. And it was sort of a solution in search of a problem. They were looking desperately for cool things to do with this new tool. And here come the meteorologists who say, well, we already have an interesting problem to solve, and this would be the perfect, so it was a perfect match. And in fact, it's a little bit like now with AI, which we realize it's a cool tool. We are looking desperately for really useful things to apply to. And so this happened, and this picture is a good example. Here, in the same picture, you see Jules Charny, who is a famous climatologist, and von Neumann, who is one of the inventors of modern digital computer theory. So, and there are different experts of computing and climate and meteorology together in this picture. And so they worked together, and they were able to do the first skillful forecasts of the weather using digital computers. They were more skillful, and I mean, Richardson also tried it, by the way. He did it. They did a little calculation. It failed miserably. They were not able to predict the weather even a few hours in advance. That they were integrating, unfortunately, the wrong equations, too complex equations. They were smarter here. They used a much simpler version of the equation, a hyper-simplified version, which still was able to produce maps of the weather, which were sort of reasonable. Okay, but here we are dealing now with climate. Don't confuse weather with climate. Weather is about predicting if tomorrow I need a raincoat. Climate is not about that. Climate is knowing if in a few years, summers will be typically more rainy or less, or more, if I will have higher temperatures here in the city of Torino, or humidity will increase or not, or what will be the variability, but never specifically for a specific day. It's not that I will it's impossible to predict weather because it's chaotic, farther than, say, 15 days in advance is basically impossible. So then we go to climate. We need we go about the statistics of the system. So now let me concentrate on climate models. The climate model follows exactly this scheme. It takes the world, takes the atmosphere, takes the oceans, divides them in a grid. So I will talk about spatial resolution because it depends how fine this grid is, how many grid points I have. The finer the grid, obviously, the better I resolve certain phenomena. To give you an idea, modern climate models have a resolution around 100 kilometers, okay? So now, thinking of your applications of interest, particularly if you think of things, say, in an urban setting, for example, you might wonder, well, but a city is much smaller than 100 kilometers by 100. And that's indeed a problem, and I'm coming to that. You do this for the world, you do this for the oceans, for the atmosphere, you do it for the oceans, you do it also in the vertical. Then you you have the famous equations of motion. Of course, this is just a decoration, don't worry. You have the famous equations, and you transform them into computer code. You use this approximation technique to integrate them, and this basically is your climate model. This would have been only ocean and atmosphere. The problem is, so here at this point it becomes just an issue of having a powerful enough computer to solve these equations and get our simulations. And the more powerful computer I have, the finer the grid I can make, and I can also increase the resolution. And I can also make more model simulations, of course. The problem is more complex though, because the climate system is actually composed of many different components. I only mentioned the ocean and the atmosphere. But of course, it's way more complex than that. We have vegetation. If I do a future climate projection and I predict that it will be raining less at the border of the Sahara, well, maybe the vegetation which is currently there will die. And so, and this will feed back on the climate system itself. So in theory, a good model should have some way to represent this phenomenon, so should have active vegetation. In the atmosphere, we have a chemical composition. We have aerosols transforming into each other. Aerosols have an important effect on climate. A good, sophisticated model should represent also this. So you see, there's a lot of components. A volcano erupts, puts a lot of aerosols in the stratosphere. That's maybe something I want to represent in my model. Sea ice floating on the ocean. I mean, the examples are infinite. So we need to put all these components in the models. And in fact, you might see there are two terms, global climate model, which nowadays is often used mostly also for the basic model, climate, atmosphere and ocean, or Earth system model, which means a model which is more complete, has all these additional components, and possibly does what is sort of the holy grail, close the carbon cycle, meaning models everything. Because by closing the carbon cycle, I can finally do simulations end-to-end, where I just change the emissions of greenhouse gases, and the model will tell me what will be the concentrations. Nowadays, this is done slightly differently, prescribing the concentrations in many cases. Many models already close the carbon cycle, though. So, facing all this complexity, of course, the community responded by developing a broad range of models. Also because, as I told you at the beginning, the needs are different. And so we range from very simple models, so-called energy balance models, etc., to the complex Earth system models up here. And basically, they're different, both in terms of the number of components which are represented, and also in terms of the level of detail, say the resolution which they achieve. And just to give you an idea of how a modern climate model looks like, just a horrendogram, basically, of the interactions, but it's like different boxes. It's an atmosphere model, an ocean model, etc. They're all connected. They work together, and they're basically separate models. And there's a lot of development work in each of these components. I mean, typically a model, this is an example, it's a model I'm working with, ECEARTH. ECEARTH is a model which uses the best, one of the best models for the atmosphere, which is a model of the European Center for Mid-Range Weather Forecasting. And uses an excellent ocean model, but it also has an interesting active vegetation model, which was developed by yet another group, and so on. So you see that these modern models are very complex and are built through the effort of many different groups. I can do different things with these. I show you only, let's say I show you only this slide. This is an example of future projections obtained from different models. And what I'm showing you here in this slide is actually future projections by models of different types. The CMIP5, those are models from 10 years ago, and many different models were giving me a projection of what would happen in a quite extreme scenario in the future here in Europe, both in terms of temperature and precipitation. CMIP6 is the latest release of this model, so they are probably better in terms of resolution, they're better in terms of components. And Cordex, these would be yet another type of model I didn't talk about. Those are regional models, models which work only over a given region, but the advantage is that they can achieve a higher resolution. Question to Giacomo, can you tell me what time I should end? Okay, good. I'm relaxed more. Yeah, okay, something like that. Okay. Okay, so this plot, which comes from a study a couple of years ago, shows us how there has been a change and evolution in what the models project, thanks to these advancements. And we would hope that actually they give us a more reliable projection, but, well, that's subject to study, of course. It certainly tells us that there is huge uncertainties in these models, because each model will give me a different projection. So, little piece of advice, never ever trust a single climate model. always consider a little ensemble of them, at least, well, more than one at least. I'm a little bit uncertain on this statement because then soon I will show you very high resolution models, which obviously at the moment we have only one or two, and so I'm contradicting myself. Of course, it's not only the basic, the sort of essential climate variables which can be projected by these models, but at that point you can derive all the indicators you want. So for example, here there's cooling degree days or maximum temperature change, precipitation, maximum temperature, precipitation during one day, frequency of droughts during a decade, etc., etc. I mean, these are all possible outputs of such models, and you can understand how these can be used also to make impact assessments or to drive further models. I mean, you can have another model which uses the output of these models to work. There's a problem. I told you that the models have been getting better, and in fact, during recent years, the resolution has been increasing. Just to say, in 1990, the average resolution of the models was 500 kilometers. 500 kilometers means that basically almost you don't have the Mediterranean represented. And then more recently, we come to 100, or in some extreme cases, 40 kilometers for some experimental projects. Then things have gotten, then there is another class of models, which is these regional models, which nowadays has operationally come to, well, the experimental runs, which go to higher resolution, but the basic archives you find will be around 10 kilometers, something like that in terms of resolution. Don't believe that a model is better if it has a high resolution. A model might have a high resolution, but be very bad in terms of reliability of representing reality. It might have what we call huge biases. So it's not always that a better model is a higher resolved one. It's clear that if you live in a country like Italy, for example, which is very narrow, well, a little bit more resolution to represent the Alps or to represent this country might help. Then the models have gotten better also over the decades. Again, this is a story which starts actually from the 70s. Also in terms of components. You see, the first climate models only had an atmosphere, and nowadays we have come to having models which have atmosphere, ocean, all those components which I listed earlier. So, better models in two directions. There's actually good argument to have better resolved models, to increase resolution, and now I will focus on this. There have been different studies, there have been different projects also, which in the past have tried to increase the resolution. Typically, they started in years where the typical resolution of the models was 150 kilometers or something like that, and they've tried to increase that down to, say, 25 kilometers or something like that at best. But already this exercise has shown that we can expect huge improvements. Well, certainly you represent better topography, so all topographic effects in the models are better represented. You improve the representation overall, apparently, of the water cycle, particularly the transport of humidity and such phenomena are better represented. And then a lot of phenomena which are related, don't look at the details, I mean, many of these are very technical terms, but many phenomena related to the to extremes and to the variability in the models are certainly better represented when you increase resolution. One of the reasons for that, let me skip a couple of slides, is this, is what we call parameterizations in the model. Parameterizations, by the way, in Italian would be parametrizations, in English is parameterization, but since the models have a coarse resolution, anything which happens below this resolution cannot be represented explicitly. 100 by 100 kilometers, think of the last thunderstorm you have experienced, say, yesterday. If you happen to look at the radar map, you might have noticed that the thunderstorm cell covers a part of the city of Torino, typically. So it's much smaller than 100 kilometers on one side. So, cells 100 by 100, how many thunderstorm cells I can have? A lot. So the models need to represent this, but still a thunderstorm takes a lot of warm, humid air and puts it up higher in the atmosphere. So it has an important effect in terms of the general circulation of, etc. So we need to represent thunderstorms in the models, even if we cannot model thunderstorms. So parameterizations are empirical, mathematical formulas which try to give you the effect of a thunderstorm, even if you cannot model it explicitly. And models differ a lot in this choice of parameterizations. And one of the interesting things is that, of course, the higher resolution you go, you start possibly to represent certain phenomena explicitly. For example, in the ocean, eddies, mid-latitude eddies, vortices, at mid-latitudes can go down to scales like 20 kilometers, something like that. If the model has a resolution which finally reaches that, you finally manage to represent these explicitly. And so many phenomena might be better represented. So there's a lot to be said about increasing resolution. There's a lot of hope that this might make better models. It's still a little bit experimental. And then increasing resolution is linked also to this other problem. As I told you, the models have a resolution of only 100 by 100 kilometers, which is totally insufficient for certain applications. So for some applications, say, typically I have worked in the past for many different applications, but say you have a specific building in a city, you're interested in knowing what happens there, well, obviously 100 by 100 will not do it. Particularly if you're interested in extremes. I work with colleagues who are hydrologists. If they have a very small basin, 100 by 100 doesn't tell them anything. They want to know what are the probabilities of having flash floods in the future. I work with ecologists who were asking me, okay, what will happen to my ibex? Well, but you know, they live on that mountain and graze on that meadow. So you see, the scales can become extremely high. And so we have this problem of jumping from these huge scales to finer scales. And one solution, which is what has been done so far, basically, is simply to increase resolution either with mathematical tools, so basically inventing what is going to happen at small scales, but in a realistic way, so to have mathematical, statistical representation of the small scales, or to do it explicitly with another climate model, a more highly resolved climate model, which are these regional climate models. The problem is that when the large-scale model has huge biases, huge discrepancies with reality, the fine-scale model, the regional model, cannot correct that typically. So there's a lot of problems with this two-step approach. Nowadays, there's an argument for actually increasing a lot the resolution of the global models. And we can finally dream to do it, or actually we are doing it, because we have extremely powerful computers now. And so we can use this brute force approach to simply increase the scale of the global models down to a few kilometers. Notice that basically I'm talking about a jump of almost 2 orders of magnitude. Before I told you about 100 kilometers, now we're jumping to 5 kilometers, 4 kilometers. We aim in a couple of years to do regularly even 2.5 kilometers. It's amazing how we can jump. And also, this is linear, but in terms of computational expense, remember that it's in one direction, but there's also the other direction, so it's quadratic. So if I increase resolution by 20 times, the computation cost is 400 times more. I also need to decrease the time step for numerical reasons, so it's even more. So it's really an amazing development. There is a lot of arguments why high kilometer scale global climate models could be useful and necessary. Here's a short list. Many of them are basically technically, but you could think of them in these terms. In the end, the representation of extremes, particularly at a local scale, should be improved. And this is what we hope. And it's both true in the atmosphere, but it's true in the ocean. And in general, we also hope that the biases of the models might be reduced. There's some indication, because if you look at, these are the observations, and these are biases in terms of tropical precipitation. You see here's the Pacific. And this is models from 20 years ago. They still had the huge bias. And you see how further generations of models have actually gotten slightly better. Not solving the problem, but better. Here's another motivation related to the water cycle, which has been made in a paper, this paper which I cited a couple of years ago, which is about the fact that these better models, the models will, for example, be better to represent convective processes. In particular, as an example, there are these huge clusters of convective clouds, which are called mesoscale convective systems. I circled a couple of them. Those are mesoscale convective systems, so that you get the idea. And that plot shows you how much of the local precipitation is due to mesoscale convective systems in different parts of the world. And to pique your interest, if you are more interested, say, in Europe, possibly, then notice that also in Europe, there is a significant percentage which is due to that. For example, there's some flooding events in Italy which can be attributed to this phenomena. And these are completely unresolved by the current models because they do not correctly represent explicitly convection. They only parameterize it. And these huge clusters of convective cells, they are not able to represent them. So we hope this will get better. Here I have a little game for you. This is from a paper from some years ago. This is obviously more different weather models at different resolutions were asked to represent what happened on a specific day. So these are all different models. These are clouds, all different models. Can you spot one of them is a satellite observation? One is true, one is reality. Can you spot which one is reality? Any guess? It's impossible, basically. Yeah? But just for fun, some of you try. Say, okay, so you would say this one. Okay, not to make it too easy, I can tell you they put it somewhere in the middle. They did it on purpose. Another one. Then I end, of course. Just try, maybe you're lucky. The third of the second row, very close. It's actually the second of the second row. Almost, you get the consolation prize. Okay. Now, okay, the point here is that you see how different the structures are. I mean, they all look realistic, but then if you look in detail, you realize that they are not. In fact, there's a lot of studies now to make better parameterizations in these models. They are first runs at very high resolution. Okay, they're different, very quickly, there are different initiatives which are currently working on extremely high resolution modeling. One is one I'm fond of because I'm currently working in it, which is this Destination Earth. And there's another series of projects, all funded by the European Union, Next Gems, which is going to an end next year, which is developing basically these parameterizations. A German project, which is basically focusing on one specific model, but again, trying to fund its development. And this one, which is more focused on the oceans, but again, they do global simulations, so it's both. So they all work together to make it possible in the future to have a new generation of models which will have this kilometer scale resolution. And this is actually happening because this Destination Earth project, which I spent 2 minutes to discuss, has been inaugurated last Monday officially. So the data in theory now become public. And it really has its goal of creating a digital replica of the planet. Here I have this discussion of the digital twin. I already did that. It contains basically at the moment 2 digital twins. One is about climate, the one we are more interested in here. And one is actually about extremes of weather. So they take, when they have an extreme weather forecast, they have the ability to do quickly a very high resolution forecast to better assess the likelihood of having huge extremes. So that's a slightly different problem. And then associated with that, there's a huge ecosystem of services which make it possible to work with this data, particularly also to, in the end, implement applications, to implement new models. So it should become possible in the future, we already are doing it experimentally, that if you have a specific application in mind, or you have code to do it, you can port it and bring it and run it together with these models. In particular, the Destination Earth Climate Adaptation Digital Twin, here you can see how much resolution has improved. You see it. And it brings a lot of features. Well, kilometer scale models, but it's not only that. It's an entire system to work with the models. There is an innovative concept of streaming the data. I mean, these models are creating petabytes of data. It's impossible. You cannot download them to your computer and work with them. You need to work somehow closer to the machine. It's not even possible to store them all necessarily. So in some cases, it might be convenient to just have the model running. While the model is running, run already your application or use this data. so have this streaming concept. And of course, we need tools to evaluate these models. And actually, well, I put this here because we are working on that. And well, here I have just a couple of slides. These I will leave to you. I do not go into detail because I don't have time, of some of the problems we are trying to solve. And well, specifically, we are working on the diagnostics. So these are some of the problems we are dealing with. Let me skip it. This, by the way, is LUMI. We are using for this project the most powerful computers in Europe at the moment. LUMI is a pre-exascale computer, one of the 3 largest machines in Europe, or 4 machines in Europe. This one is located in Finland. The other 2 are one in Barcelona, Spain. The other one is in Bologna, in Italy, Leonardo. And of these machines, of LUMI, for example, at a certain point, we were using 15% of the resources. So that, just to give you an idea of the cost of this. And well, here's some plots. We are doing diagnostics, so I couldn't not show you some plots because I'm fond of that, but this is what we are doing. Okay. But now, let me just show you a couple of animations. So this is, which are the least scientific thing I could do. Of course, you do not do science looking at animations, but they're very cool. So we show them for that. And here you can see, for example, the increase in resolution. You see the red line. The top row is how a classical climate model. And the bottom part, the left bottom part, is what the models can do now. And it's quite amazing also what you can see in terms of this strange combination of pressure, wind, and temperature, what is shown. Look, for example, here, how you can see katabatic winds coming down from the Croatian higher plains to the sea. It's basically, we are representing explicitly the phenomenon of Bora in Trieste. And you see the difference. I mean, also in terms of impacts, applications, and so on. I mean, the difference is between having this type of data or this type of data. But enough publicity, of course. And here's another one. This one is much longer. I only show it because, oh no, wait. Okay, so then I have another couple of animations, but I can, well, we can. I wanted to conclude with showing you this, which is how this, of course, this, I said these models can now be used for impact studies. Well, already in this project, we have a group where I don't have results to show from them, but we have a group which is computing indicators for urban heat stress, human stress, from these models. Here's another example. This is about urban heat island effect. And different models, 30 kilometers, 9 kilometers, and 1 kilometer, and the difference of temperature of a pixel compared to the surroundings. And you see how the city of London, for example, stands out, but it really stands out only when you come down to 1 kilometer. At 30 kilometers, you see this yellowish blob, which is not really what you want. So you see, this is one of the needs for that. This I will skip, and well, that's it more or less. Only last thing is, where can you find climate model data? Well, for Destination Earth, I didn't have a link ready, but Google it. The data will be available or are available. There's a lot of presentations currently about this. For more classical models, I have here a couple of slides which exemplify where you should look. The Copernicus Climate Data Store is a European service which provides you climate data in sort of an authoritative way. And so that should be probably the first place where to look. And they even have now a nice atlas, so you can actually make your own maps, etc., very comfortably. And with this, I would actually conclude. Thank you.
I don't see now, so I think we can leave the word to Maria Kolokotroni.
Okay, thank you. What I would like to do today is, to some effect, is following in what Jost has been describing for us, all this amazing work about trying to predict the climate for the future, for the present as well, and what is happening in cities. So what I'm taking on is how we can now apply it in thermal energy prediction studies. So the title of my presentation is Urban Context and Climate Change Impact on the Thermal Performance and Ventilation of Residential Buildings. And I'm taking a case study building in the city of Athens. My co-authors in this paper is Mei Jun, Ted Painton from Brunel, and also the owners of the case study building in Athens from the city of Athens municipality, Ilia Christandoni and Dimitra Tsakanika. So I wanted to start with what actually Giacomo already said today, that this study is part of the PRELUDE project, and he has described it already. But what I wanted to focus is that we have got these 8 pilot buildings across Europe. And these are the images of the buildings in Geneva, 1 in Torino, Athens, 2 in Denmark, and also 1 office in Krakow. Within the project, as Giacomo said, we have a task which is about climate resilience, and here at Brunel, that he is leading, and here at Brunel, we are looking mainly at the urban dimension. So let me go now to show you the building and the case study. So this is the external view of the building. It is a residential building, which is actually it's a shelter from homeless people. And this is the typical plan of the building, where you can see the bedrooms with ensuite bathrooms and then a common space in the middle. Here are the surrounding streets, photographs of them. And here is a 3D from Google, that the red blob here is our building, and then this is the surrounding area. As you can see, it is quite a dense area with not a lot of vegetation. And in front of our building, there is a long street that crosses Athens. Actually, it starts somewhere here, which is near the center of Athens and near the Acropolis, and then it goes to the suburbs. Now, when we are doing thermal simulations for this building, usually what do we do in thermal simulation programs like Transis, Energy Plus, ISV, and so on? We use typical weather files that usually they come from the airport. And we don't take into account what is happening around the building so much, because we don't have the files. Here you can see some data from Athens, taken from the meteorological station at the airport. And here you can see that temperature-wise, there is quite high temperatures during the summer, but there are low temperatures during the winter as well. And this indicates that heating and cooling is needed, which we can also see in the heating and cooling degree days, where you can see that there is need for cooling, but there is need for heating as well. And here we can see the wind speed and direction, and we can see that the prominent wind direction at the airport is from the west. So the question is how we can use this in order to apply what is happening around the building. So in this slide, I have try to outline a methodology that we have proposed a few years ago, and one of the people that we work is Giacomo as well, and actually he was leading it together with the first author, Agnese, who is now a lecturer in Barcelona in Spain. So we have our building, which is here. And usually in a dynamic thermal simulation program like Energy Plus, we just make a model, a geometrical model of the building, usually without any of the surrounding buildings. And we use, as I said, the typical weather file usually for the airport. But we had some tools that we can modify this weather file. First, modify it according to the urban texture morphology. And this software is called Urban Weather Generator, which, if we calculate some ratios about the building, including the height, including higher the building compared to the density, and also the site coverage ratio, which is again the buildings versus open areas, then it can give us the specific urban air temperature for this area, and also the urban surface temperatures for surrounding buildings. So we take care of the air temperature and surface temperature, but we have other things that they are happening around the building. First of all, we have shading effects from the surrounding buildings, and of course solar obstruction, which will change the solar heat gains for the building, which will change the heating and cooling demand for our building. So this can be actually easily done with the dynamic thermal simulation programs, but of course we have to build the areas around the building, around our main building. And finally, and the most difficult of them, is how to take into account the wind speed. And we have our building here, surrounding buildings. The building might be in a street which is long and high, an urban canyon. And this is something that has not developed very much. We need to do more work on it, but for some cases, as I will show you, we have some ways of how to do it. So if I go to the next one, first, in order to calculate the indices to feed into the urban weather generator, we need to consider the area around our building. And usually in the literature, if we consider an area of 250 radius around the building, then it is enough to give us what is happening in the area. And then we need to calculate all these numbers here, which is a little bit fiddly, and usually using, some map of the area, Google Maps and so on. We can do these calculations and look at the vegetation and so on. Then we need to look at solar obstruction, which can calculate it from most softwares if we put the surrounding buildings. But the wind speed, as I said, it is a little bit more difficult, and the modification of the wind speed, it will depend on the ratio of the height of the buildings and the width of the road, the length of the road and the width of the road, the wind speed, and so on. And according to what these ratios are, then we can use different models in order to do our calculations. And so according to the conditions, we use the model, and then from using this model, we can predict what is the wind speed in our area hourly, given what it is the wind speed at the airport. So we did all this for this specific building in Athens. And here I wanted first to show the differences in external conditions, and we have done this for a contemporary situation now and what it will happen for a future climate scenario for 2050, and we use the RCP 8.5, which is one of the most pessimistic scenarios, but even so it seems that we are heading towards that, but we hope not. But anyway, when we look at the outdoor air temperature, dry bulb temperature, we can see, as expected, that if we take into account the urban weather, then the temperatures are higher because of the urban heat island, but the wind will not affect the external temperatures. If we go to the future, again, the future is higher than the present in terms of temperature. And then if we take the combination of urban heat island as well, we even have higher temperatures around our building. And here is the same, but only for the summer period that we can see we have a little bit of higher temperatures between now and the future. When we look here at the wind, then we can see that the urban weather modifies the wind a little bit, but not a lot. But when we take the canyon wind, we can see here that wind speeds are very, very low in comparison to the airport data. And this, of course, will affect the natural ventilation strategies for our buildings. And the same happens for the future. And the same happens for the summer as well. So, taking that into account, we run, using Energy Plus, 4 different sets of simulations, one with rural weather files and no overshadowing, one with rural weather files and taking into account shadowing, one with the urban weather generator, and one with everything, shadowing, urban weather generator, urban temperatures, and wind modification. And we did this for 2 levels in the building, a lower level and a higher level, because as we will see, this will give us some variations. So coming here to the results of the simulations, first, I will concentrate here, which is the current weather data and shaded, taking into account the shading, for level 2 and level 4, the lower and the higher floor. So we can see, as we saw in the beginning from the heating degree days and cooling degree days, that we need some heating and some cooling. In the future, we will need less heating because of the urban heat island and more cooling, again because of the urban heat island. If we look between a lower level and a higher level, we see that there is quite a bit of difference in the heat in demand, and the heat in demand is less in the upper floors because they are less shaded by adjacent buildings. So we've got useful heat gains in the winter that reduce the heat in demand. But of course, the opposite happens in the summer because we have, again, heat gains, solar heat gains, that they are not useful anymore because they increase our cooling demand. And in the future, as you see here, heating is very little comparison with today, and cooling is becoming higher and higher. If we look now at overshadowing and the urban weather, we can see what we were expecting. Heating is less, cooling is more. In the future is the same. And in the upper floors, again, heating becomes lower and lower and cooling becomes higher. And finally, when we consider everything, including the modification of the wind speed, we can see that now we need heating and cooling. But as you see here, when we used only the shaded and rural weather file, the actual now needs less heating and it needs more cooling. And the future, even less heating and more cooling. And on the fourth floor, which is the upper level, if we compare this with the file without taking into account the urban effects and the wind speed, then we can see that if we use this file, we'll overestimate the heating demand and we underestimate the cooling demand. So the point is that it is very good to modify our weather files, and especially in dense city areas, so we can predict the actual performance of the building. I have another slide here, which actually shows the monthly heating demand for level floor, the upper level. And we can see here, if we concentrate in January, we can see that our usual simulations without overshadowing effects, they predict so many kilowatt hours per square meter per month. But if we consider the shading, the demand is higher because of the reduced solar heat gains. If we take into account the urban weather file, then the demand is reduced because of the urban heat island. And if we take the urban canyon wind, the demand is further reduced because of the lower wind speeds. So the air exchange between inside and outside is less by infiltration and natural ventilation. So we have less heat in demand. What this happens for indoor air quality is a different matter, but let's concentrate on to heat in demand now. And cooling demand as well. As you see, it's the opposite. So if we concentrate on July here, what we usually do, it will give us the blue bar. If we take the shading, it will tell us that we need less cooling because we block the solar gains. But if we take the urban weather file, urban heat island into account, we go up because of the increased temperatures, and if we take the wind, we go up again because of the less air exchange, especially at night, which will cool the structure of the building. And to give you also an idea, not for heat in demand now, but what will happen if our building is free running and we don't have air conditioning, what will happen in our building. And I will concentrate only this. This is what we are going to predict now. We are going to predict that half of the hours in our building are comfortable. But if we look at the modified file with urban and canyon wind, we can see that the uncomfortable hours have increased quite a lot. And the same will happen, and this will depend on the orientation of the room, west and east. And also in the future, if we do simulation to see what happens into the future, we can see here that with the rural weather file, we predict quite a lot of uncomfortable conditions, but quarter of them are comfortable, whether while if we get the actual weather file for the site, we can see that virtually most of the time the conditions are uncomfortable in the building during the summer. So to conclude, what I presented today is that the confounding effects of urban density, urban textures, and exposure to the wind, building and design, and human activities alter weather characteristics over and around urban areas. We can generate specific weather files using programs like the Urban Weather Generator and Urban Canyon with direct calculation, which will give us more specific predictions for our building. We did this for one building located in Athens, which is one of the buildings of the PRELUDE projects. And what the simulation showed is that we have an increase of cooling demand, and in the future this increase is much higher. The total energy demand is increased only a bit for lower floors and a little bit more for higher floors due to the reduction of the heat demand. But in the future, the increase will be much higher, 32% for higher floors, but a bit lower, 13% for lower floor. And if the building is free-floating, an adaptive thermal comfort analysis indicated that only 25% of summertime will be comfortable in the future compared to 50% by the current typical weather file. So I suppose the conclusion of this presentation is that it is essential that we use suitable weather files that include urban external conditions in thermal simulation so that we have more accurate predictions of the energy demand and eternal avoidance of overheating in free-running buildings, and then we don't have complaints from the building occupants and the building operators when what we predict is not exactly what happened in reality. And with this, I conclude my presentation and thank you for your attention, and I'm very happy to answer any questions. Thank you. Thank you.
Thank you, Maria. Do you have some question? We will continue with the third.
Okay, thank you. Thank you.
The last presentation is about using different reanalysis Eurocorder climate model to be applied to buildings and build environmental issues. The presentation is shared in between me, Paolo Carrisi, the being remote connection left me to speak also in his part, and also to A.Jahanirahaei, which is both Paolo Carrisi and Ali are research fellow here at POLITO, no? One from architectural domain and one for telecommunication engineering domain to support the complexity of the elaboration. So what, only to remind and to give an idea of the background, no? We always know, and we have spoken a lot today with a lot of very interesting, I think, you can say inclusion of extra topics to what we treat like architects or general building engineer. But we know on our side that the climate directly impacts on building design and operational choices, because when we design a building, we cannot take into account the climate better. Was in the past, because we make very fantastic systems, they consume a lot and they give to us the comfort. But without arriving to that, now we clearly know since the 60s and the 70s with bioclimatics that the site condition, the climate condition, the local aspect are essential to support a correct building performance according to where a building is located. In addition to that, clearly when we pass to the building operation, so to the control logic of real building life, will not be more the climate, will be the weather that will bring us to control the system. But in the design and in the design of the control, so we use the climate to set typical local condition. And as general point of view, we always assume in these years in which bioclimatic has diffused, climate as a fixed, stable element. But as we have seen, that's not more like that. So when we elaborate on a computer tool, and when we do an analysis extracting a climate model, the risk to have a very old climate model or a very old climate data from past elaboration, or to have a climate coming from a faraway site, or with a site with different conditions. We just have seen the urban dimension by Professor Kolokotroni. This clearly gives the idea that it's very important to start understanding where we are taking the data and what they are impacting on our design, because the climate in itself is becoming a sort of dynamic, at least in the long run, parameter requiring resilient studies. That's not only about future climate, but it's also about the climate that we use. For example, if you go to the Energy Plus, where they find one of the most diffused database for IPv, we have a lot of locations in Italy. The majority of them are referring to a specific database, which is EGDG, the Gianni De Giorgio, but refer to climate of the 50s and 60s. So you can imagine how different is the requirement for cooling and heating to the one that we expect now. So if this is roughly speaking the background, it's also clearly evident that low energy technology, passive solution, and these type of things are strongly climate dependent. So, and the more we go to the cooling, passive technology, the more they are climate dependent. So in passive heating, roughly speaking, is driven by solar radiation hatches. And so in some way, location with similar distance from the pole, for example, may be considered in a similar way. On the passive cooling point of view, the weight of the pressure, the ground temperature, a certain depth, or the variability of wind velocity may be very different even at locations that have a similar global horizontal irradiation, given the fact that these aspects need to be taken into account. And if the climate data is not feasible or is not upgraded, clearly we are projecting or designing something which is not aligned with reality. So the objective of this presentation, but also of the work that we are doing inside the PRELUDE project, and is ongoing for the last months, is to support a climate dynamic correlated dimension in building performance analysis. That requires clearly the fact to develop, as required to develop new tools, able to connect building simulation with its dynamic aspect, because when we go to passive low energy, the early simulation is required. We cannot go to steady state monthly base, because otherwise we lose all the mass effect, we lose a lot of aspect in passive ventilation and so on. So we need to include dynamic energy simulation tool. We need to include a series of database of key performance indicators that allow to us a direct correlation between climate and building performance. And we will see, we will work at 3 levels. Sort of climate elaborated data for build environment, like average temperature, monthly temperature distribution, this type of things that we know all because it's correlated to the energy certification. We have virtual climate indicators. That is what? The fact that we can use, like degree days, okay? We know degree days are calculated on a climatic data, on a temperature. Does not take into account a specific building. But the degree days is linearly correlated to the heating requirement or to the cooling requirement, according if it is cooling degree day or heating degree day, with a specific slope and a base temperature. And the same for several other potential virtual building indicators. And at the end, we also have a full simulated buildings, now with all of the dynamics in Energy Plus in our case, that allow us to correct, dimension, and analyze the effect also of the operational choices. What about if the threshold of shading is given in that way? That's what we are looking also at. In addition to that, clearly we need to prepare and to bring inside this simulation tool climate databases with, for what it is possible, higher distribution of the few data valuable and current portal for buildings, and also that are able to include different periods from the past to the model of global future model that we have seen in the Jost presentation. Clearly not the last one, okay? The one that are currently available on the Copernicus data store. This requires clearly to define a new approach to hybridize this type of data for bioclimatic design analysis. is required to define this sort of risk of indicator to connect massive databases in a building simulation flow, clearly by making automatic analysis. Otherwise, with millions of simulations, we cannot manage manually, okay? And after that, we clearly need to support and perform territorial and single-site performance analysis to show the impact of this approach in built environment correlated aspect. Oh, fantastic, I lose some position of this phase, doesn't matter. So we have the methodological phases that we develop are these one, no? A series of KPIs checked, developed over the time. Several of them we directly have in the past 10 years validated on performance data in a real building and living lab. After that, we have the Copernical integration of the Copernical data store with NetCDF4 data. Single year, single variable is the way in which we store. And we have ERA 5 land, and 20 couple of global and regional model of Eurocortex. We will see today the elaboration of 4 of these couple because are couple that are complete, okay, for all of the variables that we need. Some of the other, you can say, combination, global and regional, potentially may lose for some period some of the variables, at least in the dollar. So we will add in the future 6 months. Here's clearly the Eurocortex, since the model will include the historical part from 1970 to 2005, and after the, we can say, projection in future, and we use RCP 2.6, 4.5, and 8.5 till 2100. After we generate a code inside our PREDICE tool, they produce the EPV. EPV is a format, energy plus weather format, where they require a lot of variables because we have precipitation, we have temperature, we have humidity, we have wind velocity and direction, we have global, direct, and normal and diffuse radiation. We have a lot of splitting aspects that require a post-elaboration, no, of what there is inside the reanalysis database ERA 5 and ERA 5 land, and especially Eurocortex, in which several of the variables are given a 3-hour or 6-hour interval. And these are elaborated by our tool to produce, under request, energy plus weather data for all of the locations in the downloaded maps that include all Europe. After that, we have prepared our PREDICE simulation platform to run energy plus massive simulation with sensitivity analysis and so on at territorial and single size level. Furthermore, since these require a lot of time in terms of computational efforts and also in terms of space to storing the results, no, because APV are quite expensive in terms of storage. On our point of view, we have also developed, and we are now developing a parallel, we can say, interface, which is not fully exploring all the PREDICE potential, but which is a CDO Python SCDF4 based version of PREDICE that does not elaborate the EPV, but only go to develop and to calculate the climate and the virtual building KPI that does not require the simulation. So, roughly speaking, the first point that we have is clearly the set of the KPI identification. These clearly connect, as we say, climate indicators, so heating zoning, the summer severity index according to the NEA base for the Italian and not solely on Italian databases to be further expanded in the certification, average and standard radiation, monthly dry bulb temperature. So these aspects that generally are taken into account, especially when we analyze something on a point of view of energy certification in terms of suggesting minimal requirement. Typical daily profile, clearly, so 24 hours, humidex, tropical day, tropical night, this type of index. After we pass to virtual building key performance indicator that include clearly all the aspects correlated to heating degree day, cooling degree day, heating degree hour, cooling degree hour, according to Eurostat model, to the ISO model, which are different. And so the calculation also changes and so on. We also have included all the heating and cooling degree day resilience model that include, for example, the impact of virtual barrier pipes, virtual ventilation, virtual evaporative cooling, all of these aspects, in order to give the idea of the potential of this technology on a site without running a building simulation. We have included the dissipation potential in terms of cooling or heating support, so not dissipation by integration to the heating process of barrier pipes, of ground heating and cooling solution, and of direct evaporative cooling solutions. In addition to that, we also had in the potential for heat gain dissipation of ventilation in buildings to calculate the potential of the ventilation alone without coupling with the requirement. Furthermore, we have the climate cooling potential, which is an indicator for ventilative cooling recognized also by the IEA Annex 62. And after, we have the typical Givoni charts subdivided in different type of zoning, according if you are looking for a specific technology applicability, or if you are looking for the whole impact of bioclimatic technology for pre-treating the external condition and giving summer condition, or giving winter condition and the residual heating and cooling requirement. Last but not least, clearly we have the building correlated KPIs. These directly come from the result of a dynamic energy simulation that solves sub-early a building in terms of mass, energy, balance equation, the same equation that we know generally. In this case, we use energy plus like simulation engine. And all the input of energy plus are parametrically modeled by our interface. In this case, we look operative temperature with BGT, predictive involved PPD, the adaptive comfort model if you're running the model in free running, cooling internal degree hour, heating internal degree hour, some indicator also connected with Annex 80 on the capacity to resist to its stress of the building, energy signature, heating and cooling needs, final net primary energy, and the energy signature with the identification of base temperature. As we say, one of the other issues that we have solved is the complexity for simulate this aspect. Because clearly to manage some 10,000, I don't know how many points we have in the whole Europe of Eurocorridor, but you think about 10 kilometers per 10 kilometers, so you think it's some thousand of points, no? And each time that we run it potentially for 2-3 times of potential for sensitivity on building characteristics. So that start to have some hundreds of thousands of simulation, okay, of a specific building run. So to do these things and to manage this output to be further produced in a map, clearly we have taken, you can say, advantages by the fact that in Prelude and also in a previous European project at DICE, we have developed an interface that manages energy plus like a ping-pong tool for mass sensitivity analysis simulation. So we can, given a specific building object, this IDF, and given the starting weather file, in the case of our analysis, in this case, the weather comes from the climate, for this climate analysis, we are able to manage with a JSON file a massive set of simulation. We change, the tool change all the time according to the request, the starting building model, for example, changing the insulation, changing the opening percentage, adding the shading, and so on. It runs all the time the module, collect the result, and calculate the KPI, because, you know, Energy Plus has a limited amount of KPIs, and several of them are not upgraded, for example, to European standard. So need to be post-elaborated by the interface. And this allows at the end to produce post-analysis graph and maps, like in this case. Inside this aspect, clearly, we also have into account the fact that we need to support and to analyze the climate and changing the input. So only for giving an example, this PREDICE tool is able to support as different usage scenario pre-built, okay? One is sensitivity analysis for building design choices. One is optimization of the choices. One is calibration of model for producing the digital twin. We have real-time performance gap detection in a building. So in between monitor and simulated data, identify the variation and say, we have a problem, and helping identify which part of the system is broken, for example. This type of things. But for what we are doing, clearly in this case, we perform climate analysis. And to support this climate change resilient analysis, which is the last added scenario, we also have a forecasting scenario for future building optimization. in this particular scenario, clearly we take into account the fact that we have upgraded the PV compiler that till this moment only combined typical and current monitored data of the weather connected weather station through the cloud, so real-time data integration. In this case, it's integrated and connects the possibility to produce an IPv from an HCDF4 multi-file. So clear what you do, we take an HCDF4, it passes from 3 through single hour to 6 to single hour with special complex integration algorithm, especially for solar radiation, not to not have a negative value and to have the peak when it is needed. And after that, it produces an IPv file to run this type of simulation. Clearly, to support this type of analysis, we mainly, given the IPv, we after support two types of analysis. Site analysis, so a single site, a single plot or building plot in which we have a specific building, and on that we are able to simulate this building from the 50 to 2023, okay, based on reanalysis data, and from considering the global and regional model coupled from the 70, considering the historical part of the database till the different scenario, no, of future projection. And this is quite interesting because it gives us the idea if our retrofitting choices optimized today is still valid in 20, 30 years. So if you optimize the insulation level to minimize cooling and heating needs, for example, will be this choice valid for the next 30 years, which is the payback time, for example, or we have an error. And since we already demonstrated in the previous studies that this error may be of 60, 80, 90% of the expectation, because we go to the cooling and not to the heating dimension. In some of the sites, clearly site dependent, it's clearly important to know where we are moving. After that, we are clearly supported a series of territorial studies. This is what we mainly look today, some first example and output, that is mapping of the technological applicability at this variation. We will also hope to produce in future a map of optimal U value for Italy with present and future climate. Clearly, this is done exploiting our server potentialities. So we'll now start to see some of these results. We start by ERA 5 land based results. So we are in reanalysis data, about 10 kilometers of that. But in this case, we analyze single site results. So we take Turin. We have done it for all of the demo case in the PRELUDE project, but now we see some example in Turin, trying to understand the resilience of technological choices in a specific site. First, in this case, we have a virtual building correlated result, okay? So is, roughly speaking, the number of our distribution in the well-known Givoni chart that allow us to understand, given a climate, which technology are more or less applicable on the bioclimatic point of view, which is the potential of direct evaporative cooling, which is the potential of ventilative cooling, how many times I need to shade in this location, how many times I can exploit passive heating if I have sun spaces in this location, etc. If we look in the third indicator that has residual cooling, in the 25 we have bioclimatic covered cooling, okay? 21 is comfort, 23, 22 has heating needs converted to comfort thanks to passive heating solution, 24 is residual heating. If you look at what arises in between the 50-74 typical meteorological year calculation according to the ISO standard, so the typical climate, to the more recent period in ERA 5 land for Turin, we immediately see that there is a reduction, sensible reduction, in the residual heating. So we are, roughly speaking, facing an increase in the heat. In addition to that, we have an increase in the basic comfort. Potentially, we perceive more hot in reality than what it is given even by the climate, but in any case. And after that, we have an increase of the potential of what? Of the bioclimatic technology applicability, especially for supporting the cooling, because clearly we are growing in this type of things. If we maintain and look at climate-based indicator, In this case, we have a restitution of the distribution of temperature and solar irradiation. We immediately see that the more than we go, that's reanalysis, okay? So we're not speaking about future projection, only from passing from the 50, 70 period to the last period, which is the last 15, 20 years, we immediately see that we have experienced in this 70 year a drastic growth of the heat in summer. That's fully evident if you look at the red part of this diagram. That for building is important because we also experience in our house, I think, if you live in Turin. When we move to the building correlated simulation, in this case, the building is a DOE model, ANSI-ASHRAE model for simulating shoebox approaches, is the residential one. Okay. We immediately see, okay, first graph is the heating degree day, you see a decrease, evident. In the second graph, we see the summer severity index, which is a vector in between temperature, air mass, humidity, and global horizontal irradiation. Also in this case, we see that we have a growth in the temperature especially. When we move to this iod, AWD, and alpha, which has indoor overheating degree, ambient warmness degree, and overheating escalation factor as indicator that based on a dynamic energy simulation, a building is able to give an idea of which is the risk of overheating in this building under the early simulation approach. You immediately see also in this case that the temperature, the EOD is growing, the AWD is also growing, and so roughly speaking, we are facing a hotter condition for the whole summer period. Something that is also visible when we look at cooling requirements. Final, in this case, is net energy. For cooling and heating, we immediately see that the heating is decreasing over the time and the cooling is slightly increasing. Okay. That is also evident when we plot the heating degree day over the heating energy need of the building. This may consistency of the heating degree day value. You immediately see that from the first to the last period in ERA 5 land, for all the locations that we have in ERA 5 land in Europe, we pass to a massive analysis, we immediately see that the second period has a experience, the green one you see, there is a reduction in the number of points in high heating degree day and also a reduction in the heating requirement, okay? So this is something to be reflected on when we suggest the minimal U value, for example, okay, of a building, because we need to experience also the climate change dimension. When we go to territorial results, again, in this case, we support analysis running a simulation model for all of the location, for all the points that we have, and we have these three periods, 50, 74, 75, 98, 99, 2022. The same period, in this case, we run on ERA 5 because there's less points, so it's faster, okay, to run thousands and thousands of simulation. It takes only some days. And when we look at the results, for example, in this case, we immediately see that we pass from the cooling degree day are growing. Because if we start looking at the map of the delta in between these two periods, we see that the distribution is not so homogeneous. So we have a point with incredibly increase on the cooling degree day and few points with a slight decrease. That may be due to the fact that there is some local condition or potentially there is a variation in the local point of view. But when we pass to the heating degree day, as expected, we only have growth. We have, in this case, used the two colors not for give you minus and plus, since are only a decrease in the heating degree day, what we want to experience and to underline better that the high reduction in heating degree day is seen when there is the high, where there is the highs, or where it is expected that there is the highs. Because with the increase in thermal, in the temperature, also the dimension of the highs or the snow presence in the Alps, for example, is reduced, and this is visible in the reduction of the heating degree day because the Earth became darker and absorbed more. If we want to see building simulation analysis at the European base in ERA 5 land, again, we can see for the two periods that there is a strong increase in the indoor overheating degree. So when we run this EOD analysis, it's immediately evident that we pass what general distribution and interest mainly the south of Europe to something that starts interesting in quite evident way, central to central, even to the north of Europe in this point of view. And also in the south of Europe, we immediately see a strong growth inside this, we can say, internal temperature, okay? When we run this building without it, we immediately see that the internal temperature is growing, the intensity of this cooling requirement. If we pass to Eurocorder models, and this is the last slide that we will see, we clearly pass in this case to the fact that we are analyzing model results. So we have a sort of, you can say forecasting, I don't know, but forecasting of future potential projection. In this case, we see the result of 4 of the couple global and regional climate models taken from Copernicus data store that are here, in this case, elaborated not by the PREDICE directly, by the CDO Python library that is a mimic of PREDICE without elaborating NDCDF4 to EPV, but directly going in NetCDF4. I don't know if I did well. Okay, I will continue. Okay, in this specific case, as you see, this is the type of representation that we have. So we are covering all Europe in terms of result. In this case, we have the cooling degree day. Counterintuitive is the one in red, okay? And the heating degree hour, which is counterintuitive, is the one in blue. So the heating is in blue, the cooling is in red. Give the idea where we are, hot and cold, okay? That's what we see. And these are 3 periods, an historical period from the 70 to the 1989, a far future, we can say, but mid-far future from the 50 to the 69, and the farer future from the 90 to 2100. What we immediately see is the growth in the cooling degree hour, which is very evident, and also the decrease in the heating degree hour, the one in blue bottom. If we want to enter and see the same variation, okay, but not in the Eurocorder, so current projection and models, but in the reanalysis of ERA 5 land, we also see that passing from the 50 to the 2010-2022, a similar path is also evident. A growth in the cooling degree hour in the top, and a decrease in the heating degree hour in the bottom. If we translate this in a visible delta, okay, so in the difference in between the 2 periods, we immediately see that this growth in the heating degree, cooling degree hour that we see on the top arrive a lot clearly in the hotter location of Europe, no? So north of Africa and south of Europe, but it starts to be visible also in all of the central to northern part of Europe. That is very evident. For example, looking at France, is immediately evident that we start seeing that all these 3 Eurocorder models that are compared, so these are results from the historical to the farer future, okay, for different type of projection in these different models of couple of models, we immediately see that all of these models show a strong increase. In some models, it's slightly less, but in all of the cases, if you look at France, we have at least 2 or 3 models that show very strong increase in the cooling degree hour, while if you look at the heating degree hour, we see this decrease that is also very strong in the north due to this reduction of the highs. If you look at the climate cooling potential, which is a potential for ventilative cooling, okay, in the different locations, we see again for 3 couple of global and regional model that the passages from the historical, the top, to the farer future show a decrease in the potential for the ventilative cooling in terms of absolute climate cooling potential index. But it's also very evident that the strongest of this reduction arrive where potentially, if you compare the 2, you see is in the top, in the north, when in reality, now is not so used because the temperature, okay, the potential in between, the difference between the comfort and the external temperature is very positive to ventilate, but we don't need to ventilate when outside we have -10 because we don't need to cool. Okay? So in reality, this decrease is not a decrease in the potential, but it's a decrease in the delta available. If we look at the climate cooling potential projection for all the 4 models that we have analyzed for this presentation, we immediately see the passing from the historical to the future part of the model, of the regional global model result. We immediately see that for all of the projection, we have 2.6, 4.5, and 8.5, we immediately see that there is a decrease in this potential in different sites. Ru is a north site in Denmark, we can say. Torino is in the middle. Athens, is very hot. We immediately see that the decrease is evident. And the problem is mainly for Athens and Turin, because what does it mean? That when we arrive after the 50, a lot of cooling is here required, but also the ventilation potential has reduced because the temperature is increased. So we cannot ventilate some more, only ventilate for the cooling. So we need to have extra activity. This clearly gives the idea of the aspect of climate change potential. To arrive to the conclusion, sorry, I skipped some of the analysis, we can also evidently see the fact that when we start plotting, for all of the period from historical to the future projection, in the different 2.6, 4.5, and 8.5 projection, for all of the models that we have here analyzed, you immediately see that this growth is visible on the cooling point of view. This is cooling degree hour, Cooling degree hours, immediately evident that the more the projection clearly passed from 2.6 to 8.5, the more is impacted on the climate, So this is also very evident in all of the period, but you immediately see how the condition for cooling requirement that also Maria underlined is confirmed. So to conclude, the new proposed methodology is interesting because we can combine the building dynamics with the climate variations. That's interesting to have an idea of this impact of building optimization choices. The zero KPIs is very extended, so in reality cover a lot of these aspects, try to put into account the potential of a technology with the requirement of the use of this potential, so its exploitability. And so thanks to align side by side the fact that one or another bioclimatic technology are more or less applicable, not only today, but also in the future, in which are the urgent topics that may be covered, for example, not only in building retrofit, only in the cost analysis, cost performative analysis, and optimization analysis for retrofitting choices, but also to suggest policy choice. So where we move for the minimal U value, considering the climate change dimension, for example. Clearly, what's next? We will continue the analysis. We will arrive to support shoebox building analysis for all the ERA 5 land, so through buildings. We will arrive to support some more computational analysis, more model for Eurocordex approaches to arrive to show this sort of maps and giving consistency to this analysis. So I thank you. If you have questions, I think that's the moment. Thank you. Okay, so roughly speaking, the simulation platform and the tool is able to work everywhere. Now we are showing European results because we have downloaded from the Copernicus data store Europe, like dimension. That in any case means that for Eurocordex we have 35 not elaborated terabyte of data. For ERA 5 land we have, I don't remind if 10 or something like that. And for ERA 5 is 5 terabytes or something like that, plus the elaboration. So each time we pass to a PV, this is more than double. Each time that we sort the result and we make the typical here, again, we have an increase. So we stay to this dimension for this reason, but the approach may be replicable everywhere because the data store has all the data in reality. Thank you very much. Thank you, Maria.
Thank you very much, everybody. Thanks.
Thanks. Bye-bye.
Bye. Have a good afternoon. Bye.
Yes.